Dear students, welcome to the heat and mass transfer part of this course. My name is Arul Varman and I'll be the instructor for this course or for this part of the course. Today will be lecture 1 for heat transfer, and today we will look at energy and heat units, some of the basics that are required for heat transfer, energy and heat units, latent heat and steam tables. I suppose a couple of these things you should have covered it in your previous classes like physical chemistry or even in some of your high school courses. Okay, so these are basics needed for heat transfer. And followed by those, we will look at the modes by which heat transfer happens. And we will look at a mathematical model for heat transfer via conduction, and we will solve a problem for heat transfer across a plane wall through conduction. So the basic textbook or the primary textbook used for this course is by Christy Giancopoulos. It covers all the three transfer processes, including momentum, heat, and mass transfer. I suppose you would have used this textbook for your fluid mechanics or momentum transfer that you would have seen earlier. And if you want additional references, you can refer to heat transfer by Holman. This is exclusively for heat transfer. And the third additional textbook is by Welty, Rohrer, and Foster. So it also covers all three transfer processes. Heat and mass transfer is a core subject for chemical engineering, as it lays the foundation based on which you can design process equipments. So chemical engineers are also known as process engineers, and we ultimately design these process equipments, or that's the main purpose for which chemical engineering evolved. And the sugarcane industry is a classic example for process industry. And with this example, I would want to show you the importance of heat transfer and or the number of heat exchange equipments that are involved in process industry. So in sugarcane industry, as you would imagine, first we have to get the juice from the sugar canes, and the juice is being clarified to remove the waste or the mud out of it. Right, okay, so that step is over here, but before that it goes through a heat exchange unit to raise the temperature of the juice, and the clear juice that comes out of the clarifier, it goes through a series of evaporators, of course, to remove the water out of it. And ultimately we also have a centrifuge to remove as much water out of it as possible, and finally it goes through a rotary dryer to dry the sugars. All right, and you can see this heat exchanger over here, the evaporator and the dryer. They are all heat exchange equipments, and to design those you need to know the basics of heat transfer. And another classic chemical industry is a petroleum refinery. And at the heart of a petroleum refinery is a distillation column. And this distillation column is used to fractionate the different products that are present within crude oil. And the way it works is, at the bottom of the distillation column, you have a unit called as the reboiler that evaporates the crude oil, and the vapor travels from the bottom of the equipment to the top of the equipment. And over there, so not shown here, is a condenser or a condensation unit which condenses the vapor, and the vapor the condensate, which is in liquid phase, travels from top to the bottom, right? So both these units, the reboiler and the condenser, they are a type of heat exchange units. So now you can again see that, in a different industry, heat exchange equipments are pretty important, right? And we will also see how mass transfer is involved in this distillation column. So we just saw that, vapor travels from bottom to the top, and the liquid travels from the top to the bottom. And as both of them are traveling across the distillation column, mass transfer also happens from the vapor phase to the liquid phase, as well as from the liquid to the vapor phase. Okay, so basically chemicals move from one phase to the other such that they tend to approach the equilibrium for that particular temperature. All right, so if we look at the composition of a liquid at any of these trays within a distillation column, so it will be close to the equilibrium at that corresponding temperature. All right, and that's how the fractions within the crude oil are fractionated in a distillation column. Okay, so as we travel from the bottom of the distillation column to the top, you can see that the temperature also cools down, right? And the composition, the liquid composition at equilibrium for each of these temperatures would be different as well. And that dictates that, at, for example, when the temperature is pretty high, you have bitumen at the bottom, and the volatile compounds will be present at the very top. And so, for example, you can realize that the LPG is the volatile compound that will be present at the crude oil, so that is being fractionated at the very top and the others in between. All right, okay, so you can see from these examples that heat transfer as well as mass transfer are important in chemical industries, and we should know the basics of both of these to be able to design both of these equipments. Okay, so we'll look at heat exchanger design in this part of the course if time permits, and in probably we may not cover it here, but undergraduate chemical engineers utilize mass transfer to be able to design these equipments later on, right? So what exactly is heat transfer? Heat transfer is a transfer of thermal energy from one point to the other. And why does thermal energy transfers from one point to the other? That's because energy travels from, where it is concentrated highly to a place where it is low, right? From high energy to low energy, energy transfers, all right? And temperature represents the presence of energy, right? Presence of thermal energy, right? So if temperature is high, the thermal energy in that place is pretty high, and if it is low, the temperature, and if the temperature is going to be low, right? So basically energy transfers from high temperature to low temperature, all right? So if you consider the schematic of a plane wall, where on the side 1 we have temperature 1, and at the other side we have temperature 2, and if T1 is greater than T2, So energy at point 1 is much higher than energy at point 2, and therefore energy is going to flow from 1 to 2, or thermal energy is going to flow from 1 to 2. All right. So this happens, okay, so in industries as well as, this process happens naturally as well, okay, so always there is energy transfer from one point to the other, all right. And in this part of the course in heat transfer, we would want to learn how this transfer happens and at what rate, okay, so that's the important question we'll be asking, okay, so we will look at models by which you would be able to calculate at what rate this heat transfer happens, right? Okay, and based on which you can design various equipments. And like I said, heat transfer happens naturally as well, okay, in your surroundings. And that's the reason what you learn, okay, not just heat transfer, momentum transfer, as well as mass transfer, they all happen, in us, in if you observe nature, okay, they all happen. And for that reason, what you learn as chemical engineers is or can be applied to different fields as well, okay, so that's why you see that chemical engineers or doing research in various interdisciplinary sciences. Okay, so what you learn here are processes or fundamentals for what you see happens in natural world, right? Okay, so the unit for energy is joules. Okay, so the unit for energy or the SI unit for energy is joules, and we also use calories, and the energy conversion between calories, BTU, British thermal units, and joules is shown over here, right? Okay, I think these things you should have learned in your previous classes as well. Okay, so like I mentioned, the SI unit for energy is joule. All right, and there are other units as well, British thermal units or calories too. All right. So the next basic you should know before we jump on is heat capacity. So what is heat capacity? So it's the amount of heat energy, okay, so the amount of heat energy in joule that is needed to increase the temperature of, say 1 kilogram or 1 kilomole of substance by 1 degree or 1 degree Kelvin. All right, so it's basically the energy that is needed to raise the temperature of a body by 1 degree centigrade, right? So that's called as heat capacity or a specific heat capacity, right? And as you can recognize, this is going to change from material to material, right? Some may need more energy to raise its temperature, whereas others may need very less energy to raise its temperature by a degree, all right? So it's a property of the substance or the material that we are dealing with, okay? And you multiply heat capacity by the mass of the material as well as the delta T, okay, so the temperature change, then you will get the energy that is needed to raise the temperature of a body or a material from one temperature to the other, right? So you have a mass at the bottom as well as temperature. So you basically multiply heat capacity by mass as well as delta T, then you would end up the amount of energy that is needed to raise the temperature of a body from one to the other, all right? And this is also called as enthalpy change. Okay, so this table provides the heat capacity for gases at different temperatures, all right? And what is shown over here is the mean molar heat capacity between 298 and at any temperature shown over here. All right, so what this means is, let's consider nitrogen for example. So this shows the heat capacity of nitrogen at 25 degrees centigrade, and let's consider this row 500 degrees centigrade. So 29.97 doesn't represent the heat capacity of nitrogen at 500, but it represents the mean molar heat capacity between 25 and 500. All right, so it's mean, right? So we are using a heat capacity to know the energy that is needed to raise the temperature from one to the other, right? So to be able to use there, we should know the mean heat capacity, all right, between those two temperature, and that's what you will fish from this table. Okay, so it should be clear from this problem statement shown over here. Okay, so it's about heating nitrogen gas. Nitrogen gas at 1 atmospheric absolute pressure is being heated in a heat exchanger. Calculate the amount of heat needed in joules to heat 3 gram moles nitrogen in the following temperature range from 298 to 673 Kelvin. All right, the first thing is we should go back to the table and fish out the CP for it. All right. So let's go back to the table. Okay, so the temperature is between 298 to 673. So 298 is over here and 673 is over here, and to the row of 673 we see 29.68, and 29.68 is indeed the mean molar heat capacity between these two temperatures. All right, okay, so once that has been fished out, you can plug it into this equation to get the heat required to raise the temperature of nitrogen. Okay, so here we are interested in 3 gram moles of nitrogen. Okay, so you can plug in 3 gram moles of nitrogen and the corresponding temperatures, and you will get the amount of energy in joules to raise the temperature of nitrogen from 298 to 673 Kelvin, right? Okay, and you should also know what is latent heat. Okay, so before going further, okay, and if you consider any material which for example is in a solid state, as we provide energy to it, its temperature will rise, right? And at a certain point, when it starts to melt, the temperature wouldn't change, okay, but it would absorb all that energy to change its phase from solid to liquid. And as it enters liquid phase again, so it will take up all its energy to raise its temperature from one to the other. And as you know that once it reaches the boiling point, it will change to gaseous phase. All right, but in this process, it takes a lot of energy, but there is no temperature change, but it changes phase from liquid to gas, and this amount of energy needed to convert liquid to gas is known as latent heat of vaporization. Okay, and in the gas phase as well, as we provide more energy, the temperature of gas keeps rising. Okay, so you just learned what is latent heat of vaporization. All right, so the amount of energy that is needed to convert the liquid phase or from liquid phase to gaseous phase is latent heat of vaporization, right? And we use steam tables to look at the energy of water or vapor at different temperatures. And in this column, you have different temperatures. And as you know, atmospheric pressure is 101.35 kilopascal. And that's the reason when it reaches 100 degrees centigrade, the vapor pressure of water at 100 degrees centigrade is equal to atmospheric pressure, and hence boiling happens. All right. Okay. As therefore, at 100 degrees centigrade, if someone asks you what is the amount of energy needed to change water from its liquid phase to vapor phase, you go to this row and find out the energy of vapor, okay, so which is over here at 100 degrees centigrade, and the energy of liquid over here. So you take the difference between both. That tells you the amount of energy that is needed to convert water from liquid phase to vapor phase, right? So this happens at atmospheric pressure, but if you lower the pressure of that unit, then it will boil at a much lower temperature, right? So if water boils say at 50 degrees centigrade at a low pressure of 12 kilopascal approximately, then the latent heat of vaporization would be the difference between these two numbers. All right. Okay. And if you consider the liquid phase alone, if someone asks you how much of energy is needed to raise its temperature from a T1, let's say 12, to a T2 that is 80, then what you have to do is fish out this number 50.41. That was the energy of water at 12 degrees centigrade, and the energy of water at 80 is 334. The difference will tell you the amount of energy that is needed to raise the temperature of water from 12 to 80 degrees centigrade, and this is all for per kg. Okay, I hope this kind of clarifies how you would have to use steam tables. All right. Okay, so let's look at an problem. Okay, so that can explain you further, or clarify the doubts you may have further. Find the enthalpy for each of the following cases: heating 1 kg water from 21 degrees centigrade to 60 degrees centigrade at 101.325 kilopascal. All right. So it's basically raising the temperature of water from 21 to 60 degrees centigrade. So you want to find out the enthalpy of water at 21 and 60 degrees centigrade. Okay, to be more precise, if you want to be more precise, okay, so which is 21.11. So you have to use interpolation to find out the energy of water. Okay, so at 21.11 it would be close to 88, right? Let's see, at 21.11, as you can see, it's closer to 88 kilojoules per kilogram. And from here at 60 degrees centigrade, its enthalpy is 251. All right, 251. Okay, so the difference between these two provides the amount of energy needed to raise the temperature of water from 21 to 60 degree. All right. Okay. And the next problem is about heating water from 21.11 to 115.6 and vaporizing it at 172.2 kilopascal. All right. Okay. So basically, yeah, the pressure of that unit is very high, and therefore it boils at a very high temperature. All right. Okay, so you want to know the amount of energy needed to to change water from 21.11 to a vapor at 115.6 degrees centigrade. All right. So the energy of water or the enthalpy of water at 21.11 is shown over here. And for the final state, which is vapor at 115.6 degrees centigrade, you have to fish out from the table on what the enthalpy of vapor would be at 115.6. It will be closer to 269, 2699, and that's what we have here. And the difference between those two numbers would provide you the answer, all right, to change the water from a liquid at 21.11 to a vapor at 115.6. Okay, right. And so this is what changing from a liquid state to a vapor state. And part C is exclusively about vaporizing, all right, vaporizing it from water at 115.6 to one at the same temperature, okay, but change of state, all right. So how much energy is needed? So what you have to do is just fish out the enthalpy of a liquid and the vapor at that temperature 115.6. Okay, so it should be closer to these two values, and you can see here, okay, so one value closer to the other, closer to 482, and then this one again is closer to 2699. Okay, so the difference provides us the latent heat of vaporization at that temperature. All right, I hope these examples clarify how to use the steam table. All right, so what are the three modes by which heat transfer happens? And I think you should have learned these in your high school courses as well. Okay, so there are three modes. Okay, so conduction, convection, and radiation. Okay, and like we have seen previously, heat transfer happens because thermal energy at one point will be higher than thermal energy at another point, which is represented by its temperature, right? So heat transfer happens, and when heat transfer happens in a solid, so we call it as a conduction, or specifically heat transfer by conduction happens due to the random motion of its constituent atoms, molecules, or electrons. All right, so the atoms or molecules, they vibrate. Okay, so due to their energy state, they vibrate. All right, and that motion transfers energy from one point to the other. All right, the atoms or molecules by themselves do not move from one point to the other, but as they vibrate, they transfer energy from one point to the other. Okay, so this is heat transfer by conduction, and it happens in solids, or it happens in stationary fluids as well. Okay, so there are a good example would be if we look at windows. So you will have gaseous, you will have two layers of glass, and between which gas will be a sandwich, and you can assume that the gas is not moving through that thin gap. Okay, so then heat transfer can be assumed to happen via conduction, okay, through that non-moving gas, okay, or the stationary fluid. All right, so this is heat transfer by conduction. And heat transfer via convection is the next mode of heat transfer. All right, and in this case, the fluid moves, and it carries energy. All right, so in this schematic as shown over here, so you have a fluid that is moving, and the surface, or the surface of a wall or a equipment is at a temperature Ts, which is greater than the fluid temperature of T infinity, and therefore the fluid carries energy from the surface. Okay, so heat transfer happens from the surface to the fluid. Okay, so it keeps on carrying it, right? And this is a heat transfer via convection, right? So per definition, so whenever heat transfer happens due to the combined influence of bulk and random motion for fluid flow over a surface. Okay, so here the fluid is carrying the energy, or the molecules are moving. Okay, so they are carrying as they move. Okay, and this is a heat transfer via convection. Okay, and as you can see that fluid dynamics is also involved when we look at heat transfer via convection. And heat transfer by convection can be grouped as either forced convection or natural convection, right? Say, for example, you're in a room where you're operating a fan, then you are forcing the fluid to move, all right? To say, for example, if you're cooling a cup of coffee, all right, with the fan, okay, so you are forcing the fluid to move, and it carries energy from the hot coffee to its surroundings, and therefore it cools down. That's forced convection, all right? And there is natural convection as well. Say, for example, if you are boiling water in a kettle, you're not forcing the fluid to move, but as the bottom of the kettle heats, then as you know that I know, as the temperature of a fluid increases, its density also changes, right? Its density, it becomes less dense, and therefore it moves from the bottom to the top, all right? So and therefore that sets up a fluid motion, and this is natural convection. Okay, so that way energy is moving from the bottom of the kettle to the top, etc. All right. Okay, and the third mode of heat transfer is heat transfer via radiation, and by definition it is the energy that is emitted by matter due to changes in electron configuration of its atoms or molecules. Okay, and this heat transfer happens as electromagnetic waves. So basically any surface at a certain temperature, due to changes in its electronic configuration, it is going to emit energy. All right, so energy is going to emit energy is going to be emitted by any surfaces. Okay, so and here you have two surfaces. We try to calculate the net radiation heat exchange between these two surfaces. All right, the classic example by which energy is transferred via radiation is how we receive energy from the sun. All right, so as you know, there is no media from a sun to earth. It's all vacuum, right? So you can't have energy transfer via conduction or convection. And so energy transfer happens via radiation. Okay, so this bullet point states that no physical media is required for radiation transfer. All right. So these are the three modes by which heat transfer happens. All right. Heat transfer by conduction is given by Fourier's law, or the mathematical equation for heat transfer by conduction is given by Fourier's law. All right. Okay. So what Fourier's law states is heat transfer rate per unit area is proportional to the normal temperature gradient. Okay. So basically heat transfer rate per unit area, Qx here represents the heat transfer rate per unit area. Let me get to this area again. Okay, so heat transfer rate per unit area is proportional to the normal temperature gradient. Okay, so which is delta T by delta X. Okay, so as X changes, T changes, right? So that's your temperature gradient. Okay, delta T by delta X. So Q by A, which is also known as heat transfer flux, is proportional to temperature gradient. right? So basically, yeah, rate of heat transfer is proportional to the temperature gradient. Okay, so if this slope is pretty steep, then heat transfer rate is going to be larger, right? If this slope is not steep, okay, so if it's close to being flat, then heat transfer rate or heat transfer flux when you divide it by area becomes low, right? That's what Fourier's law states. Okay, so that's what Fourier's law states. And to remove the proportionality sign, you always know that we bring in a constant, and that constant is nothing but the thermal conductivity you all know about. Okay, so that's your thermal conductivity, okay, which is the units of watt per meter per Kelvin. And the heat transfer rate has a unit of watts, which is nothing but joule per second, right? So whenever we talk about rate, it is per second, right? So heat transfer rate is joule per second, which is also provided by watts. And in this equation, you also have a cross-sectional area, all right? So this schematic you see here is in 2D, and as you would have realized that heat transfer happens from point 1 to 2, so therefore heat transfer, let me see if I can draw here. All right, so basically heat transfer happens in this direction, right? And the area you should be seeing, the area that you should be using is the area that is normal to the direction of heat transfer. Okay, all right, so let me complete this as a 3D block, all right, or here. Okay, so I'm not that good in drawing using this pen here. Okay, so you should not be using this area. Okay, so this is very important. Okay, so this is the area that is normal to the direction of heat transfer. All right, so this is the area that you should be using. All right, okay, so it's basically let's say this is your y coordinate, and this is your z coordinate. Okay, so then basically area here represents, okay, so your delta z into delta y. Okay, so which is the area that is normal to the direction of heat transfer, right? Okay, so I hope you got everything in this slide. And another thing that you should be aware of is thermal conductivity is a function of temperature. However, for most of our problems, we will just assume mean thermal conductivity between the two temperatures we are interested in, right? Okay. So let's find out the equation to with which we can calculate rate of heat transfer across flat wall. All right, and here we call it as a steady state heat transfer. All right, so some of you may have heard this term, or some of you may not. What steady state tells you is that that particular variable doesn't change with time. All right, so for this case of heat transfer, and let's consider this flat wall at steady state, these temperatures T1 and T2 doesn't change with time. All right, and if they don't change with time, Q also doesn't change with time. Okay, that is steady state. All right. Okay, so this is a very good assumption to design equipments. Okay, so whenever chemical industries are in operation, they are at steady state, right? So for example, if a reactor is under operation, we try to maintain the contents of the reactor at its optimal temperature, right? And we can assume, okay, so for a given length of time, the surrounding temperature is also going to be somewhat steady, and therefore you have a steady state, right? Okay, or another good example would be if you're, doing heat exchange between two different fluids. See, yeah, hot oil is coming in and you're cooling it with coolant liquid, right? Both of them are going to be at a steady state. Okay, so they're going to be at a constant temperature. Okay, so these are examples of a steady state. Okay, so when we start chemical industry, so it will be in unsteady state. Okay, so when we start to operate it, it will be in unsteady state, but as over time it will reach at a steady state, and we will try to maintain the entire processes at a steady state over the length of time. And of course, as in advanced courses, you will know that there is always fluctuations that are going to happen for various reasons, and that's where another a course called as a process control comes into picture. All right, okay, so let's forget about all of those. Okay, so here I wanted to show you where a steady state fits in process industry. All right, so you can see that when in industries in operation, things are close to steady state, right? So this assumption is pretty much valid. All right, so to derive this equation, you begin with Fourier's law. All right, and you try to move delta x to the side, and delta t of course remains on this side, and you integrate it from point 1 to point 2. Then you end up with this equation, a very simple integration. All right, so where at the bottom you have the thickness of the flat wall, and at the top you have the temperature difference. All right, so you end up with this equation over here that says that Q is directly proportional to a temperature difference. Okay, so temperature difference dictates how fast heat transfer happens. Okay, and not only that, we will later see that, okay, so this delta x, k, and a can be rearranged to add a term called as resistance. All right, okay, so as resistance increases, then heat transfer comes down, right? Okay, all right, okay, so let's look at a problem and see how that equation that we just learned can be applied here. Calculate the heat loss per meter square of a surface area for an insulating wall composed of a 25.4 mm thick fiber insulating board. So delta X is given as 25.4, where the inside temperature is 352.7. Okay, so we are asked to look at the heat loss. Okay, so if we consider this to be 352.7, heat is being lost from inside to outside, and the outside is at 297.1 Kelvin. And this is your equation. Okay, so all the terms on the side, okay, so are given except for thermal conductivity, and you can use a table's thermal conductivity table. So from this book, in this book, you can look at appendix A3 to fish out the thermal conductivity, and with which you can solve for heat transfer flux. Okay, all right, so I think with this you can see how by using Fourier's law you can obtain a mathematical form to calculate heat transfer across a plane wall. I think we covered enough for lecture 1, so let's end lecture 1 with this, and we can come to lecture 2 in our plane walls in series in the next class. Thank you all.